Welcome back. In this video, we're going to solve wind and current problems using two variables. So our directions stay the same. I ask you to identify the variables, set up a system of equations in two variables, and then solve the system algebraically and answer the question. And we'll use charts again to help us out. You don't have to use the charts. If you can set up the system of equations in two variables without it, that is fine with me. Let's wind the clock a little bit. Let's recall that rate times time equals distance. And we will let capital R, and this is important, capital R will be our overall rate. And we're going to take rate, or the overall rate, and we're going to split it up into two different things. Okay, imagine yourself if you're riding your bike in a strong wind, or running against the wind, or kayaking or canoeing in a river against the current or with the current. These are the kinds of things we're going to be working with. So rate's going to be the overall rate, but then we're going to have some sort of force acting on ourselves or on whatever we're in. And we're going to let small r, lowercase r, be the rate of the object in still air or water prior to any wind or current acting upon it. So we'll let little r, that's kind of our effort without wind or current or anything. And we'll let c or w or something else be the rate of the wind or the current. So really our overall rate is somehow made up of this r and this c. So let's think about this. What happens to your rate when the wind is at your back? If you're out riding your bike and you have a nice tailwind, how does that go? Well, hopefully you realize that you bike faster. Well, mathematically, how would we express that? Well, if the wind is at your back or a tailwind, that would be expressed as your effort, little r, plus c. So that's addition. It's going to add to your speed or to your effort because it's pushing you along even faster. Whereas, what happens as you try to paddle a kayak upstream or you ride your bike against the wind? Mathematically, how does that impact your effort or your overall rate? Well, hopefully you realize that will slow you down. So our overall rate now will be r minus c, or could even be like r minus w, whatever. The wind or the current is working against you. So our overall rate really is made up of r minus c, or our overall rate is made up of r plus c, our effort plus the current. So let's take a look at this first word problem. A plane can fly 3,750 kilometers in 3 hours with the wind. The plane takes 5 hours to travel the same distance against that same wind speed. Find the rate of the plane in still air. Find the speed of the wind. Okay, so we're making this trip, we're flying with the wind. And we know that rate times time equals our distance. So with the wind, well, it takes 3 hours with, and against it takes 5 hours. It takes longer. Well, we're going to call capital R, overall rate, little r, that's the plane's speed, plus w, because we have the wind at our back. So it's pushing us along, and it's making our overall rate faster. And so against the wind would be r minus w. And this does make sense. We're going at a slower rate because we're subtracting from our effort, so it's slowing us down, and that takes more time. So our setup seems to be correct here. So our distance is 3 times r plus w, and our distance is 5 times r minus w. Well, the one-way trip is 3,750 kilometers. So this distance here is 3,750, and this distance here is 3,750. And this actually is our two different equations. Okay, we have our equation with the wind, 3 times r plus w equals 3,750 miles out. And then 5 times r minus w equals 3,750 miles back. So those are our two equations. And I encourage you to resist the temptation to distribute. Many high school students want to distribute that 3 right away or that 5 right away. That's okay. It will work. But it's much easier in these problems. You will find that our equations are generally going to be divisible. So if I divide by 3, I'm left with r plus w equals 1,250. And if I divide by 5, my second equation, I don't have any distribution here. I end up with r minus w equals 750. So my two equations, I've rewritten them, and linear combination or elimination works really well here because I have equal and opposite coefficients on my wind. So my w is going to drop out. So I have to remember, though, if I'm going to add these two, r and r is 2r equals 2,000, and we divide by 2, and we get r equals 1,000 kilometers per hour. We have just found our rate in still air, or our effort. Now, to find the wind speed, that's really quite easy. We can take our r and we can plug it into either one of these two. So r is 1,000, so we get 1,000 plus w equals 1,250, and all you boys, all of you can eyeball that, and we get a wind speed of 250 kilometers per hour. And we've answered our questions. The second sample problem is very, very similar to the first. It has similar numbers to it and set up the same kind of way. We'll do this again. Jim can row a boat 30 kilometers downstream in 3 hours, but it takes him 5 hours to return. So coincidentally, our times here are both the same, 3 and 5. But now we're going downstream and upstream. And we fill out our chart, rate times time equals distance. I've got some times, the 3 hours and the 5 hours. My distance is 30, but distance is really going to be rate times time here. So I know my distance down is 30, I know my distance up is 30. We want to find out the rate in still water and the rate of the current. So if I'm going downstream, the current is pushing me, it's making me go faster, so I'm going to add the rate of the current to my effort. And when I'm going upstream, I'm going against the current, it's going to slow me down, so I have subtraction here. And this does make sense. This is going to be a slower speed, so it's going to take more time to go the same distance, 30 kilometers up and 30 kilometers down. So I have 3 times r plus c is my distance, up, down, and 5 times r minus c is my distance upstream, and they both equal 30 kilometers. So my one equation, 3 times r plus c equals 30. That's my equation downstream. My equation upstream. So I'm going against the current. 5 times r minus c equals 30. And as I did in the previous problem, I'm not going to distribute. I'm going to avoid that temptation. And I'm going to divide by 3. And I'm going to divide, there we go. I'm going to divide by 5. So my downstream equation will just become r plus c equals 10. My upstream equation will become r minus c equals 30 divided by 5 is 6. And now I have a new system of equations that have equal and opposite coefficients on c. So I can use linear combination. I can simply add those up. Remember, r plus r is 2r, and 10 plus 6 is 16. And we see that r then must equal 8. And all I then need to do is take my value, there we go. For r is 8. I can plug it into either one of these. I'll put it in right here. So I get 8 plus c equals 10. And we can see that c equals 2. So 2 kilometers per hour equals the current. And 8 kilometers per hour equals our effort in still water. So there's a couple good sample problems with wind and current. Again, I caution you against distributing here. It's much easier to divide and solve these using linear combination. So that wraps that up, and we will see you in class.